something extraordinary is happening 93 million miles away. Right now, as you settle in for the night, the star that gives us life is churning with incredible energy. A sunspot has appeared that rivals some of the most powerful ever recorded. But before you worry, let me assure you, you're safe, warm, and about to learn something fascinating as you drift off to sleep. Welcome, dear listener, to Sleepy Science Tales. I'm so glad you're here tonight. This channel exists for moments like this, when you want to learn something genuinely interesting, but you also need to let your mind gently wind down. Tonight's story is about the sun, about magnetic storms in space, and about how we tiny humans watch and wonder at forces far beyond our control. Before we begin our journey, if you appreciate calm, scientifically accurate bedtime stories that help you learn while you relax, please take a moment to like this video. It truly helps others find this peaceful corner of YouTube. And if you're new here, consider subscribing to Sleepy Science Tales. We explore the universe, one soothing story at a time. Share this with anyone who loves science, space, or simply needs help falling asleep to something more interesting than counting sheep. Now, let's dim the lights in your mind, take a deep breath and travel together to our nearest star, the sun. It's been there your whole life. Every morning, every day, every sunset. Constant, reliable, unchanging. Or so it seems. But the sun is not a static ball of light in the sky. It's a roiling, churning, magnetic dynamo. A sphere of plasma undergoing nuclear fusion, with temperatures in its core reaching 15 million degrees Celsius. And sometimes, the sun reminds us that it's very much alive. This is the story of one particular moment in early 2026, when astronomers around the world turned their filtered telescopes toward a region of the sun that was doing something unusual, something that made scientists use words like unprecedented and extraordinary, something that had them watching, calculating, and yes, hoping. But this isn't a story about catastrophe. It's a story about observation, about understanding, and about the delicate balance between our technological world and the natural forces of the cosmos. So settle in, get comfortable, let your breathing slow, and join me as we explore what happened when a giant sunspot turned toward Earth, and the world held its breath, not in panic, but in wonder. To understand what made this particular sunspot so special, we first need to understand what sunspots actually are, and I promise the explanation is more soothing than you might expect. Imagine you're looking at a pot of boiling water. You can see the bubbles rising, the surface churning, heat moving from bottom to top in constant motion. The sun works in a similar way, but instead of water, it's plasma, a fourth state of matter where electrons have been stripped from atoms by extreme heat. Deep inside the sun, about 1/3 of the way from the center to the surface, there's a region called the convection zone. Here, hot plasma rises, cools as it reaches the surface, then sinks back down to be reheated. This continuous churning motion creates something invisible but incredibly powerful: magnetic fields. You might have played with magnets as a child, feeling them attract or repel each other through invisible force. The sun generates magnetic fields in much the same way, but on a scale that's difficult to comprehend. These magnetic field lines loop out from the sun's surface into space, creating an invisible architecture of force. Sometimes, these magnetic field lines become twisted and tangled, like a rubber band wound too tight, when a particularly strong bundle of magnetic field lines pushes through the sun's visible surface. Called the photosphere, it suppresses the normal convective flow of heat. The result is a region that's cooler than its surroundings. And here's the beautiful part: this cooler region is still incredibly hot, about 3,700 degrees Celsius. But compared to the surrounding surface temperature of 5,500 degrees Celsius, it appears dark. We call these dark regions sunspots. Sunspots have been observed for thousands of years. Ancient Chinese astronomers recorded them. Galileo studied them through his early telescopes in the 1600s. We've learned that they come and go in an 11-year cycle called the solar cycle. During solar minimum, the sun might have no sunspots at all for days or weeks. During solar maximum, dozens might appear, but not all sunspots are created equal. Most are small, simple and short-lived. They appear, persist for a few days, then fade away as the magnetic fields that created them dissipate. These are the ordinary citizens of the solar surface. Then there are the giants. In early February of 2026, during what scientists call solar cycle 25, something began to emerge on the eastern edge of the sun. At first, it was just a dark smudge, barely noticeable, but within 24 hours, it had doubled in size, then doubled again. Within 72 hours, this sunspot designated active region for 1366, or AR for 366 for short, had grown to span more than 200,000 kilometers across the solar surface. To put that in perspective, Earth's diameter is about 12,700 kilometers. This sunspot was nearly 10 times wider than our entire planet. You could line up 10 Earths across it and still not span its full width. But size wasn't the only remarkable thing about Alpha 366. It was the structure of its magnetic field that had solar physicists paying close attention. You see, sunspots are classified by their magnetic configuration. The simplest type, called alpha, has a single magnetic polarity, like the north pole of a single magnet. Next is beta, which has two polarities separated clearly like a bar magnet with north at one end and south at the other. Then we get to the more complex configurations. Beta gamma means multiple magnetic poles distributed irregularly. These are more unstable, more prone to sudden releases of energy, but the most unstable. The most dangerous classification is called beta gamma delta. Delta means that within a single sunspot region, opposite magnetic poles are pushed together, forced into contact despite their natural repulsion. Imagine trying to push the north poles of two powerful magnets together. You can feel the resistance, the tension. Now imagine that tension existing across a region larger than Jupiter, powered by the electromagnetic forces of a star. AR for 366 was classified as beta gamma delta. This configuration doesn't just sit quietly on the sun's surface. It releases energy violently, repeatedly, and as AR for 366 rotated with the sun's turning, slowly coming into view from behind the sun's eastern edge, it began doing something that solar scientists monitor with great interest and careful respect. It began to flare. But before we talk about what happened next, let's take a moment to simply appreciate the scale of what we're discussing. The sun is so large that 1.3 million Earths could fit inside it. The energy it produces every second is equivalent to billions of nuclear bombs. And yet, from 93 million miles away, it feels like gentle warmth on your face on a spring day. We exist in a remarkably safe bubble, protected by distance by our planet's magnetic field, by the thin envelope of atmosphere above us. And most of the time, we never think about it, but occasionally. The sun reminds us that we live in a dynamic solar system, where the forces of nature operate on scales that dwarf human experience. AR for 366 was one of those reminders. Let's travel back to the morning of February 1st, 2026, and imagine we're floating in space, watching the sun with the kinds of instruments that spacecraft use. The sun doesn't have a solid surface the way Earth does. What we see as the surface is actually called the photosphere, the layer where the sun becomes opaque to visible light. It's about 500 kilometers thick, which sounds substantial. But on the scale of the sun, 1 point per million kilometers in diameter, it's incredibly thin. Like the skin on an apple. Below the photosphere lies the convection zone, where hot plasma rises and cool plasma sinks, creating enormous convection cells. Some of these cells are as large as Texas. The churning motion, combined with the sun's rotation, creates electric currents. And where there are electric currents, there are magnetic fields. These magnetic fields don't stay neat and orderly. The sun doesn't rotate as a solid body. The equator spins faster than the poles, completing a rotation about every 25 days, while the polar regions take about 35 days. This differential rotation twists the magnetic field lines like winding up a rubber band. Eventually, the tension becomes too great. A loop of magnetic field line breaks through the surface, emerging into the solar atmosphere. Where it emerges, it disrupts the normal convection, creating a sunspot. Where it loops back down, it creates another sunspot with opposite magnetic polarity. These pairs are connected beneath the surface by the magnetic field line that links them. This is how most sunspots form in pairs, with opposite magnetic polarities, relatively stable and predictable. But Alpha 366 was different from the moment it appeared. On February 1st, when it first became visible rotating around the Sun's eastern limb, it wasn't a simple pair. It was a complex, a region where multiple magnetic flux tubes had emerged in close proximity, their magnetic fields interacting, pushing against each other, creating a tangled mess of magnetic architecture. And it was growing fast. Amateur astronomers around the world who monitor the Sun daily noticed it immediately. One observer in Argentina, checking his morning images, saw a dark region that hadn't been there the previous day. By evening, it had visibly expanded. The next morning, it was twice as large again. Professional solar observatories were watching too. The Solar Dynamics Observatory, a NASA spacecraft that takes images of the Sun every few seconds in multiple wavelengths, recorded the evolution in stunning detail. In extreme ultraviolet light, you could see bright, active regions surrounding the dark sunspot-caused plages, they're called. Regions of enhanced magnetic field where the solar atmosphere is heated to millions of degrees. Time-lapse videos created from these observations are mesmerizing. You can watch the sunspot group evolving hour by hour, new spots appearing, existing spots growing, merging, separating. It looks almost organic, like watching cells divide under a microscope. But this is happening on a scale incomprehensible to human intuition. What was driving this rapid growth? Deep below the visible surface, magnetic flux was continuing to emerge. Think of it like squeezing a tube of toothpaste once you start. The contents keep coming until the pressure equalizes. Inside the Sun, there was evidently a large reservoir of magnetic energy that had been building for weeks or months, and now it was breaking through to the surface all at once. By February 3rd, Alpha 366 measured approximately 100,000 kilometers across. To an observer on Earth with a properly filtered telescope, never look at the Sun. Without appropriate protection, it would have been easily visible as a dark spot, even though the Sun was 93 million miles away. Some media reports compared it to the size of the sunspot. That caused the famous Carrington event of 1859, the largest geomagnetic storm in recorded history. That sunspot was estimated to be about 400,000 kilometers across. Alpha 366 had reached approximately half that size. Half the size of the sunspot that, 167 years ago, had created auroras visible at the equator and caused telegraph systems worldwide to spark and catch fire. But size wasn't destiny. What mattered more was the magnetic configuration. And that's where Alpha 366 showed its true nature. Solar physicists use magnetograms, images that show the strength and polarity of magnetic fields. On the Sun's surface, in a magnetogram, positive polarity appears white, negative polarity appears black, and neutral areas appear gray. Looking at a magnetogram of Alpha 366 was like looking at a Rorschach ink blot test. Black and white regions swirled together. Opposite polarities pushed into immediate contact within the same sunspot structure. This was the delta configuration, the most unstable, most energetically productive arrangement possible. And when magnetic field lines with opposite polarities are forced together like this, they want to reconnect. It's like stretching a rubber band until it snaps. The energy stored in the magnetic field gets released suddenly. Catastrophically, we call these releases solar flares. Now, you might be wondering, why should we care about a dark spot on the Sun, even a large one? The Sun is so far away. How could something happening on its surface possibly affect us here on Earth? This is where our story becomes truly interesting, because Alpha 366 didn't just sit there quietly. Within hours of being identified, it began to release energy, and the way it released that energy would create ripples literally. That would spread across 93 million miles of space to reach our planet. But I'm getting ahead of myself. Let's talk about what actually happens during a solar flare, and why these explosions of light and energy matter so much to our modern world. First, though, take a moment to breathe. Feel your body sinking into your bed or chair. The universe is vast, the forces we're discussing are immense, but you are here, safe, learning about the cosmos from the comfort of your own space. The sun will continue doing what it's been doing for 4.6 billion years. We're just fortunate enough to understand a little bit about how it works. Imagine holding to powerful magnets with opposite poles facing each other. You can feel the resistance, the force pushing them apart. Now imagine forcing them closer and closer together, the resistance growing stronger. Finally, you let go and they snap apart violently. This is essentially what happens during a solar flare, but with magnetic fields carrying the energy equivalent of billions of nuclear weapons. A solar flare is a sudden explosion of electromagnetic radiation from the sun's surface. It happens when magnetic field lines that have been twisted and stressed suddenly reconnect, releasing energy in the process. The amount of energy is staggering. A typical solar flare releases about kJ of energy. To put that in perspective, that's about 1/6 of the total energy the sun releases in 1 second. It's equivalent to millions of 100 megaton hydrogen bombs exploding simultaneously, and this energy is released almost instantaneously over the course of minutes or even seconds. The process begins when opposite magnetic field lines are brought into contact. At the point of contact, the magnetic field is so strong and so stressed that the normal structure of matter breaks down. The magnetic field lines break and reconnect in a lower energy configuration, converting magnetic energy into other forms. Some becomes kinetic energy, accelerating particles to nearly the speed of light. So the physicists call these solar energetic particles, and they stream away from the sun in all directions. Some becomes thermal energy, heating plasma to temperatures of tens of millions of degrees Celsius hotter than the sun's core, and some becomes electromagnetic radiation across the entire spectrum. Radio waves, visible light, ultraviolet radiation, X-rays, even gamma rays in the most powerful flares. This radiation travels at the speed of light, naturally, which means it reaches Earth in just over 8 minutes. There's no warning, no chance to prepare. The moment a flare erupts on the sun, 8 minutes later, we feel its effects. Solar flares are classified by their X-ray brightness in the wavelength range from 1 to 8 angstroms. This might seem arbitrary, but there's a good reason. X-rays of this wavelength are absorbed by Earth's upper atmosphere, creating the effects we'll discuss shortly. The classification system uses letters A, B, C, M, and X, each representing a 10-fold increase in energy output. A class and B-class flares are minor, barely noticeable, occurring constantly. C-class flares are small, with few noticeable consequences on Earth. M-class flares are medium-sized. They can cause brief radio blackouts at the poles and minor radiation storms that affect astronauts and satellite systems. Then we come to X-class flares. These are the big ones, the flares that get scientists' full attention. X-class flares start at a baseline energy level and then scale upward numerically: X1, X2, X3, and so on, with each number representing a flare 10 times more energetic than X1. The largest flare ever recorded was estimated at X28, which occurred in November 2003, but was so powerful that it saturated the instruments measuring it. On February 1, 2026, at 23:57 UTC, ARFA 366 produced an X8.1 flare. Let me paint the picture of what this means. Somewhere within the magnetic tangle of ARFA 366, field lines that had been stressed beyond their breaking point suddenly reconnected. In an instant, the region lit up with extreme ultraviolet radiation and X-rays. If you'd been watching through specialized instruments at that moment, you would have seen a brilliant white flash on the sun's surface. A burst of light so intense it briefly outshone the rest of the visible solar disk. In those wavelengths, the Solar Dynamics Observatory, watching continuously, recorded the event in exquisite detail. Images taken in the 131 angstrom wavelength, which shows plasma at about 10 million degrees Celsius, revealed an explosion of energy rippling outward from the flare site. 8 minutes later, traveling at the speed of light, this radiation reached Earth. The first thing it encountered was our atmosphere, specifically the ionosphere layer between about 60 and 1,000 kilometers altitude, where solar radiation is energetic enough to ionize atmospheric gases normally. The ionosphere contains a relatively stable population of free electrons, created by the sun's steady ultraviolet output. These free electrons do something interesting. They reflect radio waves at certain frequencies, specifically high-frequency radio in the 3 to 30 MHz range. This is why you can tune an HF radio in Sydney, Australia, and pick up a station broadcasting from London, England. The radio waves don't travel in a straight line through space. They bounce off the ionosphere, back to Earth's surface, bounce again, reflect again, hopping across continents and oceans. But when an X8.1 flare's worth of X-rays and extreme ultraviolet radiation hits the upper atmosphere, it dramatically increases the ionization. Suddenly, instead of reflecting radio waves, the ionosphere absorbs them. Communications cease. On February 1st, when the X8.1 flare's radiation arrived, the entire sunlit hemisphere of Earth experienced this effect, but it was particularly severe over the South Pacific, which was directly facing the sun at that moment. In Australia, ham radio operators attempting to make contacts found their signals disappearing. Maritime communication channels went silent. Aircraft crossing the Pacific, which rely on HF radio to maintain contact with air traffic control when beyond the range of line-of-sight VHF systems, experienced communication loss. This is called a radio blackout. Classified on a scale from a 1 minor to a 5 extreme, the X8.1 flare created an R3 strong radio blackout. For most people, this was invisible. Your cell phone works on entirely different frequencies and technologies. Your internet comes through cables or satellites. But for certain industries, aviation, maritime shipping, emergency services in remote areas, amateur radio operators, the blackout was very real. And it lasted for hours. Even after the flare ended, even after the X-ray flux returned to normal levels, the ionosphere remained disturbed. The excess ionization takes time to dissipate as electrons gradually recombine with ions, a process that can take an hour or more depending on altitude and severity. This was just the first effect of the flare. The immediate effect, traveling at light speed, arriving in 8 minutes. But there was something else accompanying this particular flare, something that travels much more slowly, taking days to arrive, but potentially far more impactful. A coronal mass ejection. As you lie there listening, take a moment to marvel at the fact that we can know about these events at all. We've placed satellites in space specifically to watch the sun. We've developed instruments that can measure things invisible to human eyes. We've built global networks to share this information in real time. 100 years ago, we barely understood what the sun was made of. Now we can watch its surface in multiple wavelengths, track eruptions as they happen, and predict their arrival at Earth with reasonable accuracy. It's a testament to human curiosity, to our drive to understand the cosmos we inhabit. But understanding isn't the same as controlling. And as AR-366 continued to evolve and erupt, that distinction would become very clear. There's something almost hypnotic about watching time-lapse videos of the sun's surface. Magnetic field lines emerge and twist. Plasma flows along invisible highways of force. Prominences, vast loops of material suspended by magnetism rise, and slowly fall back like cosmic fountains. It's a dance, choreographed by the fundamental forces of physics, playing out on a stage larger than we can truly comprehend. Our 4366's magnetic structure was particularly fascinating. The beta-gamma-delta configuration I mentioned earlier isn't just a classification. It represents a specific physical arrangement that creates specific behaviors. Let me try to help you. Visualize it. Imagine the sun's surface as a rubber sheet. Now imagine magnetic field lines as loops of string that emerge from below this sheet. arc up through space and plunge back down somewhere else. In a simple sunspot pair, you'd have one neat loop emerging at one spot north polarity, arcing over, and returning at another spot south polarity. But in a complex region like Alpha 366, you have dozens or hundreds of these loops emerging in close proximity. Some are small and tight, some are large and arcing far out into space, and critically, some of them have opposite polarities pushed right next to each other. When opposite magnetic polarities are close, the field lines want to reconnect. It's energetically favorable, like water running downhill or a ball rolling down a slope. The magnetic field naturally seeks the lowest energy configuration, but as long as the plasma is continuously churning, bringing new magnetic flux to the surface, the field lines are forced to remain in this high-energy, unstable state. It's like trying to hold a spring compressed. As long as you apply force, it stays compressed. But the moment you relax, it snaps back violently. In Alpha 366, the spring was being held compressed by the continuous emergence of magnetic flux. From below the surface, magnetogram images taken over several days showed new regions of positive and negative polarity appearing within the sunspot complex, adding to the tangle, increasing the stress. Solar physicists have developed sophisticated computer models to simulate these magnetic fields. They take magnetogram data as input and calculate the three-dimensional structure of the magnetic field above the sun's surface. These models produce beautiful visualizations, tracings of field lines in different colors, showing how they loop and twist and tangle. Looking at such a model of Alpha 366, you could see why it was so active. The field lines were braided together like a complex Celtic knot, with multiple points where oppositely directed field lines were in close contact. Each of these points was a potential site for magnetic reconnection, a potential flare waiting to happen. And happen they did. After the initial X8.1 flare on February 1st, Alpha 366 didn't quiet down. Over the following 72 hours, it produced 5 more X-class flares, X2.8, X1.6, X1.5, X4.2, and others still being analyzed. Between these major eruptions, it peppered off M-class flares at a rate of 1 every few hours. 14 M-class flares in a single 24-hour period. That's nearly 1 every 2 hours around the clock. This kind of sustained, high-level activity is rare. Most active regions produce 1 or 2 major flares and then calm down. As the magnetic energy is exhausted, the act of flaring releases the stored magnetic energy, allowing the field to relax into a more stable configuration. But Alpha 366 kept going. New magnetic flux kept emerging. New energy kept being pumped into the system from below. It was like a kettle that kept boiling because someone kept turning up the heat. So the physicists watching this unfold were fascinated. This was an opportunity to study magnetic reconnection and energy release processes on a scale impossible to reproduce in any laboratory. Every flare provided data spectroscopic measurements showing the temperature and density of the plasma, X-ray timing showing the evolution of the energy release, radio observations revealing the acceleration of particles. But they were also concerned, because with each flare came the possibility of something more, a coronal mass ejection. You see, when magnetic field lines reconnect during a flare, they don't just release radiation and accelerate particles. Sometimes they also throw material plasma off the sun's surface and into space. Imagine a stretched rubber band snapping. The two ends fly apart, right? Similarly, when magnetic field lines reconnect, they can whip upward, carrying plasma with them, flinging billions of tons of solar material away from the sun at speeds of hundreds or thousands of kilometers per second. This is a coronal mass ejection, or CME, and CMEs are where the story shifts from merely interesting to potentially consequential for Earth, because while the electromagnetic radiation from a flare arrives in 8 minutes and then is done absorbed by our atmosphere, effects lasting at most a few hours, a CME is a physical object traveling through space, and when it arrives at Earth, typically 1 to 4 days after being launched, It can interact with our planet's magnetic field in ways that have much more sustained effects. The X8.1 flare on February first did produce a CME, coronagraph images from spacecraft like the Solar and Heliospheric Observatory SOHO showed a bright structure expanding away from the Sun shortly after the flare. Analysis suggested it was partially Earth-directed, but partially is key, because Alpha 366 was still near the eastern limb of the Sun at that time, still coming into view, as solar rotation carried it around from the far side. Any CME it produced would be aimed off to the side, not directly at Earth. A glancing blow, astronomers said, enough to graze our magnetosphere, perhaps produce a minor geomagnetic storm and some nice auroras, but not a direct hit. But Alpha 366 was still rotating. Every hour, it moved a bit more toward the center of the Sun's visible disk as seen from Earth. And the center of the disk is where Earth-directed happens. The geometry is simple. If a CME erupts from a sunspot that's directly in the center of the Sun as we see it, that CME expands outward in all directions, including directly toward us. If it erupts from a spot on the limb at the edge of the visible disk, the CME expands to the side from our perspective. By February 4th, Alpha 366 was approaching optimal Earth-facing position. Within 24 to 48 hours, it would be as directly aligned with Earth as possible during its transit across the visible solar disk, and it was still flaring, still releasing energy, still showing no signs that its magnetic complexity was resolving. If you're feeling a bit drowsy now, that's perfectly fine. Let the technical details wash over you like waves. The key thing to understand is this: the Sun had produced a region of incredible magnetic complexity, and that region was rotating into a position where anything it threw at us would be aimed squarely at Earth. The dance of magnetic fields was approaching its most critical phase, and we, 93 million miles away, were watching with instruments, with models, with hope that the dance would remain merely beautiful rather than becoming dangerous. Before we go further into what happened with Alpha 366, let's take a moment to appreciate something remarkable. Earth has a shield, an invisible, protective magnetic field that deflects most of the solar wind and the energetic particles that the Sun constantly hurls into space. Without this shield, life as we know it couldn't exist. The Sun doesn't just shine light, it constantly streams particles into space. A wind of charged protons and electrons flowing outward at speeds of 300 to 800 kilometers per second. This solar wind fills the entire solar system, creating what's called the heliosphere, the region of space dominated by the Sun's influence. When this wind encounters Earth, something beautiful happens. Our planet has its own magnetic field, generated by the motion of molten iron in the outer core, deep beneath our feet. This field extends far out into space, creating a magnetic bubble called the magnetosphere. The magnetosphere acts like the bow wave of a ship moving through water. The solar wind, carrying its own magnetic field, hits the front edge of Earth's magnetosphere and parts around it, flowing past the planet on both sides. The boundary where they meet is called the magnetopause, and it's typically located about 60,000 kilometers on the sun-facing side of Earth, about 10 Earth radii. On the night side, away from the Sun, the magnetosphere is stretched out into a long tail that extends millions of kilometers into space. This structure isn't static. It's constantly fluctuating as the solar wind varies in speed and density. Sometimes the magnetopause is pushed closer to Earth. Sometimes it expands outward. It's a dynamic boundary between two magnetic environments, the Sun's and Earth's. Under normal conditions, this system works beautifully. The solar wind flows past, most of its particles deflected, and Earth's surface remains protected. The atmosphere also helps, absorbing any high-energy particles or radiation that do make it through. But sometimes conditions are not normal. When a coronal mass ejection strikes the magnetosphere, it's not like the regular solar wind. ACME is much denser, carrying perhaps 10 times more particles than the background solar wind. It's also faster. The fastest CMEs can exceed 3,000 kilometers per second. And critically, It carries its own strong magnetic field. When this mass of magnetized plasma hits our magnetosphere, the interaction depends crucially on the orientation of the CME's magnetic field. This is where things get interesting in a way that might help you drift off to sleep. Imagining invisible forces interacting in space. Magnetic fields have direction. We often draw them as lines with arrows pointing from north to south pole. Earth's magnetic field points from south to north actually. Earth's magnetic north pole is near the geographic south pole, which confuses people. But let's not worry about that right now. The key point is that Earth's magnetic field in the region facing the Sun points northward. If a CME arrives with its magnetic field also pointing northward, the two fields have the same orientation, they're parallel, and when same orientation magnetic fields meet, they don't couple well. They slide past each other. The CME's impact is minimized. But if a CME arrives with its magnetic field pointing southward opposite to Earth's field, something called magnetic reconnection can occur at the magnetopause. Remember magnetic reconnection from our discussion of solar flares? The same process can happen between the CME's field and Earth's field. Field lines from both sources connect, creating a direct magnetic link between the CME and Earth's magnetosphere. Through this connection, energy and particles from the CME can flow into Earth's magnetosphere. The magnetopause gets compressed, pushed closer to Earth. Charged particles are funneled along Earth's magnetic field lines toward the poles, where they collide with atmospheric gases and create auroras, and electrical currents are induced in the magnetosphere, in the ionosphere, and critically, in the ground itself. These ground-induced currents are where the potential danger lies for our technological infrastructure. But let's stay with the magnetosphere a bit longer, because what happens during a geomagnetic storm is genuinely beautiful to imagine. As the CME strikes and the magnetosphere compresses, the magnetic field lines on the night side of Earth, the long tail I mentioned, become stretched and stressed. Eventually, they can snap back in a process called a magnetospheric substorm. When this happens, energy that had been stored in the stretched field lines is suddenly released. Particles are accelerated down toward Earth's atmosphere, primarily in a ring around the magnetic poles called the auroral oval. These particles, mostly electrons and protons, slam into oxygen and nitrogen atoms in the upper atmosphere at altitudes between 100 and 400 kilometers. The collisions excite the atmospheric atoms, bumping their electrons into higher energy states. When those electrons fall back to their normal state, they release light. Oxygen atoms emit green light at 557.7 nanometers, the most common aurora color. The shimmering green curtains you see in photographs from Alaska and Norway. At higher altitudes, oxygen can emit red light at 630 nanometers. Nitrogen produces blue and purple hues. The result is one of nature's most spectacular displays, the aurora borealis in the northern hemisphere, aurora australis in the southern hemisphere, dancing curtains of light rippling across the sky, sometimes covering the entire visible dome of heaven. During intense geomagnetic storms, the auroral oval expands toward the equator. Auroras that are normally only visible near the Arctic and Antarctic circles can be seen at much lower latitudes. During the Great Geomagnetic Storm of May 2024, auroras were visible as far south as Florida and Texas, and during the Carrington event of 1859, they were visible in the Caribbean. Imagine standing outside on a clear night during such an event. The sky above you, normally dark and star-filled, is alive with color. Green waves rippling like curtains in a breeze, red glows pulsing slowly, sometimes rapid, flickering movements, what observers call active aurora. Sometimes slow, stately arcs stretching from horizon to horizon. It's beautiful, ethereal, a direct visible connection between Earth and the Sun, mediated by invisible magnetic fields and charged particles traveling at thousands of kilometers per second. But it's also a sign that Earth's magnetosphere is under stress, being buffeted by forces from 93 million miles away. For the magnetosphere itself, this isn't a problem. It's designed by nature to handle this. It flexes, compresses, springs back. The auroras are a pressure release valve, a way for the system to dissipate energy. But we've built a technological civilization that exists within this natural system, and our power grids, satellite networks, and communication systems weren't designed with space weather in mind. Not originally, anyway. So while the magnetosphere protects us, and it does, remarkably well, there are second-order effects. Induced currents in the ionosphere create electric fields in the atmosphere. Those fields couple to the ground, and on the ground we've built millions of miles of conductive infrastructure, power lines, pipelines, fiber optic cables with metal components, railway tracks. Long conductive structures in a varying magnetic field act like antennas, picking up induced currents, and those currents can cause problems. This is why space weather matters. Not because solar flares or CMEs can directly harm us Earth's atmosphere and magnetosphere inshore. They can't. But because the side effects of these events can interfere with the technologies we've become dependent upon. ARFA 366 had already sent one CME our way, scheduled to arrive on February 5th. That one was expected to cause only minor effects, a G1 geomagnetic storm, the lowest level on the scale. But the Sunspot was still active, still in a beta-gamma delta configuration, still producing flares, and it was rotating into the perfect position to send another CME directly toward us. If that happened, if a major CME launched while ARFA 366 was in optimal Earth-facing position, the effects could be significantly more serious. Not catastrophic, necessarily, but serious enough to warrant close attention from the people responsible for keeping the lights on and the satellites functioning. The shield would protect us, as it always had, but shields can only absorb so much before the stress starts to show. Imagine, if you will, a cloud, not the wispy, delicate clouds that drift lazily across our summer skies, but something far grander, a cloud the size of continents, perhaps even the size of Earth itself. Now imagine this cloud is not made of water vapor, but of something more exotic, electrified gas so hot it glows, threaded through with invisible magnetic fields that twist and loop like cosmic yarn. This, in its essence, is a coronal mass ejection. The name itself is wonderfully descriptive. Coronal refers to the corona, the sun's outermost atmosphere, that shimmering, ethereal halo you might glimpse during a total solar eclipse. Mass ejection is equally straightforward, the sudden expulsion of material into space. But these simple words belie the extraordinary physics at play. CMEs are born from the sun's magnetic field, that invisible force generated deep within our star by the churning motion of electrically charged plasma. Near sunspots, those dark, relatively cool regions on the solar surface, magnetic field lines become twisted and tangled, coiled like springs under increasing tension. The sun's rotation, its convective churning, and the natural instability of magnetic structures all contribute to this winding. Eventually, something has to give when a CME erupts. It's not a violent explosion in the traditional sense. There's no shockwave in the vacuum of space, no sound to mark the event. Instead, imagine a bubble of magnetized plasma simply lifting off. The magnetic field lines that were holding this material in place suddenly snap and reconfigure, releasing their cargo into the solar wind. The sun burps, if you'll forgive, the informal metaphor, sending billions of tons of matter streaming outward into the solar system. What makes CMEs particularly fascinating is how different they are from their more dramatic cousins, the solar flares. A flare is a sudden, intense burst of electromagnetic radiation light across the entire spectrum, from radio waves to gamma rays. Flares travel at the speed of light, reaching Earth in about 8 minutes. They're quick, bright, and immediate in their effects. CMEs, by contrast, are the tortoise to the flare's hare. These massive plasma clouds lumber through space at speeds ranging from a leisurely to 150 kilometers per second to, in exceptional cases, over 3,000 kilometers per second. Even at their fastest, they take anywhere from 15 to 18 hours to traverse the 150 million kilometers between Sun and Earth. More typically, the journey takes 2 to 3 days. Scientists track these cosmic travelers using specialized instruments called coronagraphs, essentially telescopes that create an artificial eclipse by blocking out the sun's brilliant disk. The large-angle and spectrometric coronagraph LOSCO aboard the Solar and Heliospheric Observatory SOHO has been watching the sun since 1995, creating an artificial eclipse within its instruments to reveal the normally invisible corona. When ACME erupts, LOSCO sees it, a bright, expanding structure billowing outward from the solar limb, sometimes appearing as a halo if it's heading directly toward Earth. The anatomy of ACME is complex. At its leading edge, compressed solar wind piles up like snow before a plow, sometimes forming a shock wave that can accelerate particles to nearly the speed of light. Behind this compressed region comes the main body of the CME, the ejector, carrying with it the twisted magnetic field structure that was once rooted in the sun's surface. This magnetic field is crucial, for it is frozen into the plasma, a phenomenon physicists call frozen in flux. Traveling as an inseparable companion to the matter itself, not all CMEs are created equal. Their danger to Earth depends on several factors: their speed, their mass, their direction, and perhaps most importantly, the orientation of their magnetic field. A CME might contain anywhere from a few billion to over 1 trillion kilograms of matter. That sounds enormous, but remember the scale. The sun loses about 1.5 million tons of material every second through the solar wind, and it has done so for billions of years without noticing. What makes some CMEs more hazardous than others? Direction matters greatly. The sun erupts CMEs in all directions, but only those aimed more or less at Earth pose any risk. Even then, the magnetic field orientation becomes critical. Earth has its own magnetic field, a protective bubble called the magnetosphere. When ACME arrives, if its magnetic field points southward opposite to Earth's northward pointing field, the two can connect through a process called magnetic reconnection. This opens a door, allowing energy to flow into our magnetosphere. If the CME's field points northward, matching Earth's own field, the two might gently slide past each other with minimal interaction. Tracking CMEs is an exercise in patience and calculation. Once spotted by coronagraphs, space weather forecasters feed observations into sophisticated computer models that attempt to predict the CME's path, speed, and arrival time. It's rather like hurricane forecasting, but with fewer data points and a less well-understood medium. The solar wind through which CMEs travel is not uniform. It has fast and slow streams, density variations, and its own magnetic structures. A CME might accelerate, decelerate, or even collide with previous CMEs, creating merged structures with unpredictable properties. This is why, even with our fleet of spacecraft watching the sun, space weather forecasting remains as much art as science. We can say a CME is coming, estimate its speed and trajectory, but the final details, will it hit us squarely or deliver a glancing blow? What is its magnetic orientation? How will it interact with Earth's environment? These questions often remain unanswered until the CME arrives, and so these clouds drift through the void, silent and invisible to the naked eye, carrying with them the sun's magnetic secrets. Most pass by harmlessly, their effects limited to beautiful auroras at high latitudes, but occasionally, as in the case of active region AR 366 in early February 2026, the sun sends something more substantial our way, a reminder that we live, as we have always lived, at the mercy of our stars' moods. While the world slept or went about its daily business in early February 2026, something invisible was happening. High above, in the ionosphere, that electrically charged layer of atmosphere between 50 and 600 kilometers altitude, the very structure of our air was being rewritten by radiation from the sun. Most people never noticed. Why would they? Their phones still worked, their Wi-Fi still streamed videos, their conversations continued uninterrupted. But in certain specialized facilities, maritime communication centers, aviation control towers, amateur radio stations, and military installations, operators noticed something wrong. Certain frequencies, particularly in the high-frequency HF bands between 3 and 30 MHz, were simply gone. This is the invisible face of solar activity, the radio blackout. Active region AR-366 produced not just one, but multiple X-class flares over several days, powerful bursts of electromagnetic radiation that raced from Sun to Earth at light speed. These flares were classified by intensity, an X1 flare, an X for 0.2, even a powerful X8.3 eruption that ranks among the strongest observed. Each released energy equivalent to millions of thermonuclear weapons, though broadcast as light rather than explosive force. The X-rays and extreme ultraviolet radiation from these flares reached Earth in 8 minutes, long before any associated coronal mass ejections. This radiation doesn't reach the ground, our atmosphere absorbs it, but it dramatically affects the ionosphere, that crucial layer where radio waves bounce and bend. Under normal conditions, the ionosphere is a radio operator's friend. It acts as a mirror for certain frequencies, allowing radio signals to bounce between the ionosphere and Earth's surface, enabling long-distance communication around the planet's curve. This is how shortwave radio connects continents, how aircraft communicate over oceans where there are no towers, how maritime vessels stay in contact far from land. The ionosphere exists because solar ultraviolet radiation continuously strips electrons from atmospheric atoms and molecules, creating a layer of free electrons and ions, hence the name. This process is strongest on the sunlit side of Earth and varies with altitude. Different layers designated D, E, and F form at different heights, each with different properties for reflecting radio waves. A solar flare, however, floods the ionosphere with extra energy. The enhanced X-ray radiation ionizes atoms in the low ionosphere, particularly in the D layer between 50 and 90 kilometers altitude. Normally, this layer is relatively weak, especially at higher frequencies, but during a flare, it becomes dense with free electrons. Here's the counterintuitive part. More ionization doesn't mean better radio propagation. In the low ionosphere, increased electron density means increased absorption. The radio waves that were bouncing nicely off the higher layers now get absorbed by the enhanced D layer before they can complete their journey. It's like trying to shine a light through increasingly murky water. Eventually, none gets through. The effect is called a sudden ionospheric disturbance, SID, and it lives up to its name. Within minutes of a flare's X-rays arriving, HF radio communications on the sunlit side of Earth can degrade or vanish entirely. The blackout affects the entire day side of the planet, roughly half of Earth at any given moment. For most modern civilians, this is merely an inconvenience or goes unnoticed entirely. Satellite communications, cell phones, and internet connections use different technologies and frequencies that aren't affected the same way. But for certain critical systems, HF radio remains essential. Transoceanic flights rely on HF radio when they're beyond the range of VHF communications, and satellite systems. When AR-366 unleashed its strongest flares, pilots and air traffic controllers found certain communication channels unusable, forcing switches to backup frequencies or alternative communication methods. No aircraft was endangered. Protocols exist for exactly this scenario, but it required attention, coordination, and quick thinking. Maritime vessels, particularly those in remote waters, similarly depend on HF radio for weather updates, distress calls, and routine communication. During the blackouts, captains found themselves temporarily isolated, cut off from shore stations and other vessels. Emergency frequencies remained monitored, but the normal chatter of maritime radio fell silent. Amateur radio operators, ham radio enthusiasts, noticed immediately. These dedicated hobbyists monitor solar activity closely because it directly affects their ability to make long-distance contacts. During major flares from AR-366, operators on the day side of Earth saw their signals simply vanish into the ionospheric murk. Online forums filled with reports: complete blackout on 20 meters. All bands dead from 10 through 40 meters. Brutal conditions today. The military, too, felt the impact. Despite advanced satellite communications, HF radio remains a critical backup system and is still used for certain applications. During the February 2026 event, Exercises had to be adjusted, communication plans modified, alternative systems brought online. Each blackout lasted only as long as the flare's enhanced radiation continued, typically minutes, to perhaps an hour or two. As the flare subsided and the ionosphere gradually returned to normal, radio propagation recovered. But with AR 366 producing multiple strong flares over several days, these blackouts came in waves, a periodic reminder of the sun's power to reach down and shuffle our technological capabilities. What's particularly interesting is how localized yet global these effects are. Localized in that only the daylit hemisphere experiences the blackout, the night side, where the ionosphere is already reduced, continues relatively normally. Global in that the entire day side is affected equally. There's no place to hide from the sun's radiation. The official space weather scales classify radio blackouts from a 1 minor to a 5 extreme. The multiple X-class flares from AR 366 produced a 3 strong to a 4 severe conditions significant, enough to cause operational impacts but not the worst possible. And a 5 event, like the X-28 flare observed in 2003, can cause a complete HF radio blackout on the entire sunlit side of Earth for hours. It's worth pausing to consider how different this is from most natural hazards we face. A hurricane, earthquake, or flood affects a specific region. A solar flare affects half a planet simultaneously. And there's no ducking out of the way if you're on the day side when the flare hits. You're in the impact zone. Yet for all their dramatic classification names, these radio blackouts represent more annoyance than catastrophe in our modern world. They're a reminder of our technological vulnerability, yes, but also of our redundancy and adaptability. When one system fails, we switch to another. When HF radio goes dark, we use satellites. We use lower frequencies, we wait. In a way, radio blackouts are the sun's most polite disruption brief, predictable in their behavior if not their timing, and resolved simply by waiting for the ionosphere to calm down. They're a gentle reminder that our technology, for all its sophistication, still depends on layers of ionized gas floating high above our heads, and those layers, in turn, dance to the sun's tune. To understand solar storms and their potential impact, we must journey backward through time, not just decades, but more than a century and a half, to September 1859. It was late summer in England, and a gentleman astronomer named Richard Carrington was engaged in his regular occupation, observing and sketching sunspots from his private observatory in Redhill, Surrey. The morning of September 1st, 1859 was like any other for Carrington. He had been tracking a particularly large group of sunspots, carefully projecting the sun's image through his telescope onto a white screen, where he could safely observe and sketch the dark spots. It was painstaking work, requiring both patience and precision. As he documented the sun's ever-changing face, then, at 11:18 a.m., something extraordinary happened. Carrington saw two patches of intensely bright white light appear in the midst of the sunspot group. These brilliant points blazed with such intensity that they were visible, even against the sun's bright surface. Carrington watched, transfixed, as these lights evolved and intensified over the course of about 5 minutes before fading away. He immediately recognized the significance. So striking was the event that he rushed to find someone else to verify what he'd seen. Though by the time he returned with a witness, the lights had faded. That evening, Carrington wrote, while engaged in the forenoon of Thursday, September 1st, in taking my customary observation of the forms and positions of the solar spots, an appearance was witnessed which I believe to be exceedingly rare indeed. Carrington had witnessed one of the most powerful solar flares ever observed, now called a solar white light flare because it was visible in regular light, not just in specialized wavelengths. But the real show was yet to come. 17.5 hours later, shortly after midnight on September 2nd, the night sky began to behave most strangely. Across North America, Europe, and even as far south as the Caribbean, the northern lights erupted with unprecedented intensity. But these were not the usual curtains of green and red confined to polar regions. These auroras blazed so brightly that people could read newspapers by their light at midnight. In the Rocky Mountains, gold miners woke at 2 a.m. thinking dawn had arrived and began preparing breakfast. The colors were extraordinary. Blood-red auroras dominated the skies over much of the United States and Europe. Brilliant green, purple, and white lights danced overhead. In Havana, Cuba well within the tropics, people watched in amazement as the sky lit up with curtains of colored light. Even more remarkably, similar auroras appeared in the southern hemisphere, visible as far north as Santiago, Chile. But the auroras were merely the beautiful face of something more ominous. Across the world, wherever telegraph systems existed, chaos erupted. Telegraph operators reported sparks leaping from their equipment. Papers littering telegraph offices caught fire from the sparks. Some operators received electric shocks from their equipment. Instruments that were disconnected from their batteries continued to operate, powered solely by the electrical currents induced in the long telegraph wires, by the geomagnetic storm. In one famous account, the telegraph operators between Boston and Portland found that they could disconnect their batteries entirely and still communicate for 2 hours, using only the current induced in their lines by the storm. They carried on a conversation powered entirely by the aurora-generating currents flowing through Earth itself. Other reports were more alarming. Telegraph offices in Washington, D.C. and Philadelphia reported their equipment catching fire. In Norway, telegraph operators had to take their equipment offline to prevent damage. In Sweden, telegraph pylons gave off sparks. The entire global telegraph system, Victorian society's equivalent of the internet, was disrupted for days. What exactly happened? The geomagnetic storm of 1859, now called the Carrington event after its observer, was likely caused by one or more powerful CMEs hitting Earth squarely. The solar plasma slammed into Earth's magnetosphere with tremendous force, compressing it and injecting enormous amounts of energy into the system. This caused geomagnetically induced currents (GICs) to flow through Earth's crust and, consequently, through any long conductors like telegraph wires. The magnitude of the storm was extraordinary. Measurements of Earth's magnetic field, which were being made at various observatories, showed disturbances so large that they pushed magnetometers off their scales. Modern analysis of these records suggests the storm may have been twice as intense as any geomagnetic storm. Measured in the space age. Ice core records provide additional evidence. When extremely energetic solar particles hit Earth's upper atmosphere, they create radioactive isotopes like beryllium-10 and chlorine-36, which then fall to Earth and get trapped in ice and tree rings. Analysis of ice cores from Greenland and Antarctica show a spike in these isotopes around 1859, confirming the intensity of the solar bombardment. But the Carrington event wasn't a single storm. Modern analysis reveals it was actually a complex, multi-phase event. A moderate storm had already disturbed Earth's magnetic field on August 28th to 29th. Then came the massive CME from Carrington's flare, arriving less than 18 hours later, extraordinarily fast even by modern standards. This second CME plowed into a solar wind already disturbed by the earlier eruption, creating the perfect conditions for an extreme geomagnetic storm. Here's what makes the Carrington event particularly significant for our modern age. In 1859, our electrical infrastructure consisted entirely of telegraph systems, relatively simple, localized networks of wires connecting individual offices. Today, our civilization depends on vast, interconnected power grids spanning continents, along with countless satellites, GPS systems, telecommunications networks, and computer systems, all potentially vulnerable to geomagnetically induced currents and solar radiation. A Carrington-class event today would face a very different world. The National Academy of Sciences produced a report in 2008 estimating that a Carrington-level storm could cost $1 to $2 trillion in damage in the first year alone, with recovery taking 4 to 10 years. The report warned of potential widespread power grid failures, transformer damage, satellite loss, and disruption to GPS, telecommunications, and financial systems. Yet we must be careful not to sensationalize. Space weather scientists emphasize that the Carrington event, while extreme, was not unprecedented in Earth's history. And there's no reason to believe it represents the absolute worst-case scenario. Ice core and tree ring records suggest even larger events have occurred in the past millennia, though thankfully not in the industrial age. Moreover, we are not the helpless Victorians of 1859, marveling at mysterious auroras and sparking telegraphs. We have early warning system spacecraft positioned between Earth and Sun that can detect CMEs and give us hours or days of notice. We understand the physics of space weather. Power grid operators have protocols for disconnecting transformers or shedding load. During extreme geomagnetic storms, satellite operators can put spacecraft into safe modes. We have, in short, the ability to prepare and respond still. The Carrington event serves as a reminder. It shows us that the Sun, for all its life-giving warmth and regularity, is capable of outbursts that can reach across 150 million kilometers of space and touch our technological civilization. It reminds us that our star is not merely a constant yellow disk in the sky, but a roiling, dynamic ball of plasma prone to violent releases of energy. When we observe events like Alpha 366 in February 2026, a sunspot region that produced multiple X-class flares and several CMEs, we inevitably wonder, could this be another Carrington? The answer so far has always been no. The flares have been powerful, but not quite at Carrington levels. The CMEs have been significant, but not delivered square hits with perfectly aligned magnetic fields. We've seen strong auroral displays, radio blackouts, and minor geomagnetic storms, but nothing approaching 1859. Yet each event like Alpha 366 serves as both a test of our monitoring systems and a reminder that a Carrington-class event will happen again someday. We don't know when: next year, next decade, next century. So the physics has not yet advanced to the point where we can predict such things with any precision. But we know the Sun is capable of it. We've seen the evidence in ice cores and tree rings. We've read the accounts of sparking telegraphs and worldwide auroras. We know it's not a question of if, but when. And so we watch, we prepare, and we hope that when the next great solar storm does arrive, we'll be ready. If the Carrington event were to occur today, it would not be greeted with Victorian wonder at beautiful auroras and curious telegraph malfunctions. Instead, it would represent one of the most serious natural disasters in modern history, not through direct harm to human beings, but through disruption to the technological infrastructure upon which our civilization has come to depend absolutely. Let's start with the power grid, for it is here that our vulnerability is most acute and most dangerous. Modern electrical grids are marvels of engineering, connecting power plants and consumers across vast distances through networks of transmission lines, substations, and transformers. These grids operate at increasingly high voltages, sometimes exceeding 765 volts, to minimize energy loss during transmission. The higher the voltage, the more efficiently electricity travels long distances. But this efficiency comes with a hidden vulnerability. During a severe geomagnetic storm, rapidly changing magnetic fields induce electric currents in any long conductor, including Earth's crust and the long transmission lines of power grids. These are the geomagnetically induced currents, or GICs, and they pose a significant threat to grid infrastructure. GICs are quasi-direct currents, essentially DC power flowing where it shouldn't. Power transformers are designed to handle alternating current AC, not DC. When GICs flow into transformers, they cause a phenomenon called half-cycle saturation. The transformer's magnetic core becomes saturated on one half of the AC cycle, dramatically reducing the transformer's efficiency and causing it to draw large amounts of reactive power. The transformer begins to heat up, vibrating and humming ominously. Protective relays may trip, thinking there's a short circuit or equipment failure. But the real danger is more insidious. The heating caused by GICs can damage the transformer's internal insulation, particularly if the storm lasts hours. And here's the critical point: large power transformers are not mass-produced commodity items. They're custom-built, enormous pieces of equipment that can weigh hundreds of tons. A single transformer might cost several $1 million and take a year or more to manufacture and deliver. Major utilities typically don't keep many spares on hand. They're simply too expensive and specialized. The March 1989 Quebec blackout provides a sobering case study. On March 13, 1989, a severe geomagnetic storm struck Earth. Within 90 seconds, the entire Hydro-Quebec grid collapsed, plunging 6 million people into darkness. The blackout lasted 9 hours, but the full recovery of the grid took weeks as damaged equipment was assessed and repaired. What happened? The storm-induced GICs caused multiple capacitors in the grid to fail. This led to a sudden loss of reactive power support. Voltage instability cascaded through the system. Protective relays, doing exactly what they were designed to do, began tripping circuits to protect equipment. Within a minute and a half, the entire network had fragmented and shut down. Fortunately for Quebec, the damage was mostly limited to capacitors and other supporting equipment. The main transformers survived, but it could have been worse, much worse. A more intense or longer duration storm might have caused permanent transformer damage. And unlike 1989, when neighboring grids could supply power during recovery, a Carrington-class event would likely affect multiple interconnected grids simultaneously across North America or even entire continents. The implications are sobering. Modern life without electricity isn't merely inconvenient, it's existentially threatening. Within hours, hospitals would rely on backup generators. Within days, fuel supplies for those generators would dwindle. Water treatment plants would fail. Sewage systems would back up. Food refrigeration would cease. Communication networks would falter as backup power ran out. The economic impact would be staggering. A 2017 study published by Lloyd's of London estimated that a Carrington-level event today could leave 20 to 40 million Americans without power for weeks or even months. The economic cost could reach $2 trillion, roughly 10 times the cost of Hurricane Katrina. But the power grid isn't our only vulnerability. Consider satellites, those artificial stars that have become integral to modern life. Satellites face multiple threats during major solar storms. Enhanced solar radiation can damage sensitive electronics, degrading or destroying spacecraft. The heated atmosphere during geomagnetic storms expands upward, increasing atmospheric drag even at satellite altitudes, and potentially causing satellites to lose altitude or tumble out of control. Charging effects from solar particles can cause electrical arcs that damage components. We lost at least 40 satellites during a moderate solar storm in February 2022, when SpaceX's Starlink satellites encountered unexpectedly high atmospheric drag shortly after launch and couldn't reach their proper orbits. A Carrington-class event would likely damage or destroy dozens, perhaps hundreds of satellites. The loss of satellites would have cascading effects. GPS, which we use for far more than just navigation, including timing for financial transactions, telecommunications synchronization, and precision agriculture, could be degraded or unavailable for days or weeks. Communications satellites might fail, disrupting everything from internet service to television broadcasts. Whether satellites would go offline, ironically blinding us to conditions during the storm's aftermath. Earth observation satellites used for everything from crop monitoring to disaster response would be lost. Aviation would face serious challenges. Airline routes over polar regions would need to be avoided due to heightened radiation exposure and potential communication blackouts. GPS-dependent navigation systems might be unreliable. Communication with aircraft, particularly over oceans, could be disrupted. Airlines could lose millions per day in diverted flights, delays, and route changes. Even underground, when not safe, pipelines for oil, natural gas, or water can experience corrosion problems from GICs flowing through the pipes and their cathodic protection systems. While not immediately catastrophic, this could lead to long-term integrity issues and potential leaks. The financial system would face disruption. High-frequency trading relies on precise GPS timing. International transactions depend on satellite communications. The failure or degradation of these systems could freeze trading or create opportunities for errors and manipulation. During major storms, Some financial institutions have protocols to suspend certain types of algorithmic trading until conditions normalize, yet for all these vulnerabilities, we're not defenseless. Power grid operators have become increasingly aware of the GIC threat and have implemented monitoring systems and operational procedures to mitigate risks. During geomagnetic storms, these include real-time monitoring of GIC levels in transformers and transmission, Linus procedures to reduce power flow through vulnerable corridors during storm, strategic placement of jig-blocking devices that filter out DC currents while allowing AC power to flow, improved forecasting that gives operators hours or even days of warning before a storm, or a stockpiling of critical spare equipment. Satellite operators similarly have hardened newer spacecraft against radiation and developed protocols for placing satellites into safe modes during storms. GPS systems have been upgraded with better ionospheric models to maintain accuracy even during disturbances. The key difference between 1859 and today is not that we're more vulnerable, though we certainly are, but that we have the ability to see storms coming and take protective action. The fleet of solar observing spacecraft, Solar Dynamics Observatory, SOHO, Stereo, and others continuously monitor the Sun. NOAA's Space Weather Prediction Center issues forecasts, watches and warnings. Power grid operators, satellite controllers, and airline dispatchers all have protocols for responding to space weather alerts. The real question is whether we've done enough. A 2019 report by the U.S. Government Accountability Office found that while awareness of space weather risks had improved, implementation of protective measures remained inconsistent across the power industry. The cost-benefit calculations are difficult. How much should we spend preparing for an event that might happen tomorrow or might not happen for decades? This is the modern paradox. We have built a technological civilization of unprecedented capability and interconnection. This same interconnection, this complexity, creates vulnerabilities our ancestors never faced. The telegraph operators of 1859 dealt with sparking equipment and interrupted messages. We would face continent-wide blackouts and satellite failures. Yet we also possess something those Victorian observers lacked: understanding. We know what causes space weather. We can see it coming. We can, if we choose, prepare for it. The question is whether we will demonstrate the foresight and political will to invest in protection against a threat that is certain to materialize eventually. Even if we cannot predict exactly when. Active region 4366, with its multiple X-class flares and Earth-directed CMEs, serves as a useful test and reminder. It's not the big one, not Carrington Redux, but it's significant enough to test our monitoring systems, our forecasting capabilities, and our response protocols. Each such event teaches us something, refines our models, and hopefully motivates continued investment in prediction, protection, and preparedness. Because someday, perhaps tomorrow, perhaps in a generation, the Sun will hurl something truly exceptional our way, and on that day, we'll learn whether we've prepared wisely or must face the consequences of our technological ambition colliding with natural forces we cannot control. High above Earth, silent in the vacuum of space, a fleet of robotic eyes maintains their tireless vigil. They never blink, never sleep, never look away. Hour after hour, day after day, year after year, they watch the Sun. The Solar Dynamics Observatory circles Earth in geosynchronous orbit, positioned so it maintains a constant view of our star. Every 0.75 seconds faster than your heartbeat, SDO captures complete images of the Sun in 10 different wavelengths of light, from extreme ultraviolet to visible light. Each wavelength reveals different aspects of solar activity: sunspots, flares, coronal loops, prominence eruptions. The spacecraft generates 1.5 terabytes of data every single day, all of it streaming down to receiving stations on Earth, where scientists and automated systems analyze the images for signs of dangerous activity. Farther out, positioned at the L1 Lagrange point, that gravitational sweet spot, about 1.5 million kilometers upstream between Earth and Sun, sits SOHO, the Solar and Heliospheric Observatory. Since 1995, this spacecraft has been humanity's most reliable early warning system for coronal mass ejections. Its LASCO coronagraph instruments create artificial eclipses, blocking the sun's bright disk to reveal the dimmer corona where CMEs are born. When ACME erupts and begins its journey earthward, SOHO sees it first. Giving forecasters crucial lead time, these spacecraft are the sentinels of the space age. But they're not alone in their watch. On the ground, a network of solar observatories spans the globe. Some are professional facilities with sophisticated equipment. Others are operated by dedicated amateurs whose passion for solar observation rivals that of any. Career scientists dot at the Daniel K. Inouye Solar Telescope in Hawaii, the world's most powerful solar observatory of 4 meters. Mirror focuses sunlight with unprecedented clarity. The telescope can resolve features on the sun's surface just 20 kilometers across. Remarkable when you consider the sun is 150 million kilometers away. Astronomers use this instrument to study the fine structure of sunspots, the magnetic field topology that gives birth to flares and CMEs across the world. Dozens of smaller observatories contribute to the global watch. Some focus on specific wavelengths, like hydrogen alpha telescopes that reveal solar prominences and filaments with exquisite detail. Others monitor the sun in white light, tracking sunspot evolution and occasionally catching the rare white light flare, like Carrington witnessed. But professional scientists aren't the only watchers. A vibrant community of amateur solar observers contributes meaningfully to our understanding of solar activity. Armed with relatively modest equipment, often specialized hydrogen alpha telescopes, or white light solar filters attached to backyard telescopes, these enthusiasts monitor the sun daily, sketching sunspots, photographing prominences, and reporting observations to databases and online communities. When active region 4366 rotated into view in late January 2026, amateur observers were among the first to notice its rapid growth. Online forums filled with images and discussions. AOFA 366 has doubled in size in 24 hours. This region looks angry, definitely CME productive. Watch for activity. These amateurs didn't just observe for personal satisfaction, many contribute their observations to professional databases, helping fill temporal gaps and providing ground truth verification for satellite data. The network of watchers extends underground as well. Magnetometers buried in bedrock around the world continuously measure Earth's magnetic field, detecting the perturbations caused by geomagnetic storms. These instruments provide real-time data about the severity of ongoing storms and help validate predictive models. When ACME arrives and begins buffeting Earth's magnetosphere, it's the magnetometer network that tells us just how hard we're being hit. Ground-based radio telescopes also play a role, monitoring the sun for radio bursts associated with flares and CMEs. These radio observations provide information about particle acceleration and shock wave formation, crucial pieces of the space weather puzzle. Then there are the rheometer networks, instruments that measure cosmic radio noise absorption in the ionosphere. During solar particle events, energetic protons rain into the polar regions, enhancing ionization and increasing radio absorption. Rheometers detect these changes, providing warning that a radiation storm is underway. Coordinating this diverse array of observer spacecraft, professional observatories, amateur networks, and ground-based instruments requires substantial infrastructure. Organizations like NOAA's Space Weather Prediction Center serve as clearinghouses for data and focal points for forecasting. The center receives data streams from dozens of sources, feeds them into predictive models, and issues forecasts, watches, and warnings to stakeholders around the world. The human element of this watching network deserves emphasis. Behind every spacecraft, every instrument, every data stream, there are people, scientists, engineers, forecasters, and enthusiasts who have dedicated their careers or their passion to understanding and monitoring the sun. They maintain instruments, develop new observation techniques, refine models, and stand ready to interpret what the data tells them when the sun acts up. When AR 366 erupted with its first major flare, it was these watchers who raised the alarm. Spacecraft detected the flash of X-rays. Automated systems identified the flare's magnitude and location. Human forecasters reviewed the data, assessed whether ACME had been launched, and began formulating predictions about whether and when it might impact Earth. Amateur observers shared real-time images of the active region. All of this happened within minutes of the flare's peak, with alerts flowing out to power grid operators, satellite controllers, airlines, and anyone else who might be affected. The watching continues 24 hours a day, 7 days a week, without holidays or breaks. Space weather doesn't observe weekends. The sun doesn't shut down at 5 p.m., and so the vigil continues, shift after shift, orbit after orbit, image after image. There's something almost meditative about this continuous observation. The sun changes constantly, yet follows patterns the 11-year cycle of solar maximum and minimum, the 27-day rotation period that brings active regions around to face Earth again and again, the reliable daily rhythm of sunrise and sunset. Yet within these patterns, surprises lurk. A seemingly quiet region can erupt with violent flares. A massive sunspot group can rotate across the disk without producing any significant activity. Prediction remains more art than pure science. The watchers have seen astonishing things. They've witnessed X-28 flares that pushed instruments off scale. They've watched CMEs collide in space, merging into larger structures. They've observed the sun during solar minimum, when weeks might pass without a single sunspot, and during solar maximum, when dozens of active regions crowd the solar disk simultaneously. They've also learned humility. Despite all our instruments, all our data, all our sophisticated models, the sun still surprises us regularly. AR 366 was forecast to be active, yes, but the sheer intensity and frequency of its flares caught some observers off guard. The exact trajectory of its CMEs remained uncertain until they actually arrived. The magnetic field orientation critical for determining storm intensity couldn't be confirmed until spacecraft actually measured it. This is why the watching continues. Why we keep launching spacecraft and maintaining observatories and encouraging amateur observers. Every event teaches us something new. Every surprise reveals a gap in our understanding. Every successful forecast validates our models, while every miss highlights what we still need to learn. The watchers are our first line of defense in an age where our civilization has become vulnerable to solar storms. They cannot prevent the storms, nothing can, but they can see them coming, give us time to prepare, and help us understand what we're facing. In a very real sense, they stand guard between our technological society and the natural fury of our star. And so they watch, the spacecraft with their unblinking eyes, the scientists with their instruments, the amateurs with their passion, all united in the same purpose to see what the sun does next and give humanity the warning. It needs to weather whatever our star sends our way. Predicting what the sun will do is, in many ways, harder than predicting terrestrial weather. At least on Earth, we have thousands of weather stations, dozens of weather satellites, centuries of historical data and well-understood physics governing how air masses, moisture, and temperature interact. Even so, weather forecasts beyond about 7 days remain notoriously uncertain. Now imagine trying to forecast the weather on an object you can't send instruments into, whose interior you can't directly observe, whose magnetic field is far more complex than Earth's, and where the fundamental physics involves plasma behaviors that are only partially understood. Welcome to space weather forecasting. The challenge begins with the sun itself. While we can observe the sun's surface, the photosphere, and its outer atmosphere, the corona, quite well, we cannot see into the solar interior where the magnetic field is generated. We observe sunspots appearing on the surface, but we can't see the magnetic flux tubes rising from deep inside the sun until they break through. This is like trying to predict earthquakes without being able to monitor the fault lines underground. You're always reacting to symptoms rather than observing causes. When a sunspot region does appear, forecasters assess its complexity, size, growth rate, and magnetic configuration. Certain characteristics correlate with increased flare probability, rapid growth, Complex magnetic topology, regions where opposite magnetic polarities come close together. Mathematical formulas and increasingly sophisticated machine learning models ingest these observations and produce probabilities: a 75% chance of N-class flares, a 35% chance of X-class flares. But these are probabilities, not certainties. A region that looks quiet might suddenly erupt. A region that looks explosive might rotate across the disk without producing any significant flares. The sun doesn't read our forecasts, even when a flare does occur. The next challenge is determining whether it launched a CME. Some flares produce CMEs, others don't, and the correlation isn't perfect. Forecasters must wait for images from coronagraph instruments, looking for the telltale brightening and expansion that signals an eruption. This can take 30 minutes to a few hours' time, during which uncertainty reigns. Once a CME is confirmed, the next question becomes, is it Earth-directed? CMEs spread out as they travel, so a direct hit isn't necessary for impact. But direction matters greatly. Forecasters use images from multiple spacecraft viewing the sun from different angles, when available, to construct three-dimensional models of the CME's trajectory. They estimate its speed based on how quickly it appears in successive coronagraph images. Then comes the waiting. A fast CME might take 15 to 18 hours to reach Earth. A slower one might take 2 to 3 days. During this transit time, forecasters refine their predictions as new data arrives. Is the CME slowing down? Speeding up? Has it merged with the solar wind or with other CMEs? The most critical uncertainty can't be resolved until the CME actually arrives: the orientation of its magnetic field. Remember, for a CME to drive a strong geomagnetic storm, its magnetic field needs to point southward opposite to Earth's northward field to enable efficient energy transfer through magnetic reconnection. But we can't directly measure the magnetic field of a CME while it's in transit between Sun and Earth. This is where the L1 spacecraft become crucial. Positioned about 1.5 million kilometers upstream of Earth, spacecraft like DSCOVR and ACE serve as sentries, measuring the solar wind and any CMEs that pass by. When a CME arrives at L1, instruments measure its density, velocity, and critically its magnetic field orientation. This data is immediately transmitted to Earth, giving forecasters about 15 to 60 minutes of warning before the CME impacts Earth's magnetosphere. 60 minutes! That's how much advance notice we get for the single most important parameter, determining storm severity. It's better than nothing. Enough time to send out final warnings. For power grid operators to take last-minute protective actions, but it's hardly comfortable. This is why space weather forecasting remains as much art as science. Forecasters speak in probabilities and scenarios. A CME was observed. If Earth-directed, arrival could occur on February 5th to 6th. Geomagnetic storm levels could reach G1, G2 minor to moderate, possibly reaching G3 strong depending on the solar wind conditions. And CME magnetic field orientation, notice the qualifiers: if, could, possibly, depending on. This is the language of uncertainty, and it's honest. We simply don't know what will happen until it happens. Every forecast carries an implicit margin of error. The careful language serves another purpose: avoiding both complacency and panic. Overforecast too often crying wolf with predictions of major storms that fail to materialize, and stakeholders stop taking warnings seriously. Underforecast and people are caught unprepared when a real event strikes. Forecasters walk a constant tightrope between these extremes. The uncertainty isn't for lack of trying. Space weather forecasting has improved dramatically over the past few decades. Numerical models can now predict CME arrival times within a few hours. Statistical models have gotten better at estimating flare probabilities. Machine learning algorithms are being trained on decades of solar observations to recognize patterns that precede major events, but fundamental limitations remain. The sun is a chaotic system. Small differences in initial conditions can lead to vastly different outcomes. The same sensitive dependence on initial conditions that limits terrestrial weather forecasts also applies to the sun. We're essentially trying to predict the Behavior of a roiling ball of plasma, 1 point per million kilometers in diameter, threaded with magnetic fields undergoing constant flux, where the relevant physics includes magnetic reconnection, plasma instabilities, and turbulent flows that we still don't fully understand. Compare this to hurricane forecasting, which has become impressively accurate. Forecasters can usually predict a hurricane's track days in advance, within a couple hundred kilometers. Intensity forecasts are harder, but still reasonably reliable. Yet hurricanes occur in Earth's atmosphere, where we have vastly more observations and better understood physics. Solar storms occur 150 million kilometers away in a medium we can only observe remotely. The space weather forecasting community is candid about these limitations. Scientific papers regularly discuss uncertainties and errors. Forecasts include error bars and probability ranges. It's a refreshingly honest approach. Here's what we think will happen. Here's how confident we are. Here's what we still don't know. Research continues to push the boundaries. New spacecraft missions promise better observations. Advanced computer models simulate solar plasma physics with increasing realism. Machine learning tools mine decades of data for subtle patterns. Each advance incrementally improves forecasting skill. But barring some revolutionary breakthrough in solar physics, space weather forecasting will likely remain probabilistic and uncertain for the foreseeable future. We will get better at it, gradually, year by year, but we won't achieve the precision we might wish for. And perhaps that's okay. Perhaps part of our relationship with the sun involves accepting that this massive, ancient, nuclear furnace that gives us life will occasionally do things we didn't expect. At times we didn't anticipate, with consequences we couldn't fully predict. Our job isn't to achieve perfect prediction that may be impossible. Our job is to watch carefully, forecast as best we can, and prepare for uncertainty. When Alpha 366 produced its barrage of X-class flares in early February 2026, forecasters did their job. They detected the flares immediately, looked for CMEs, estimated trajectories and arrival times, issued appropriate warnings, and then waited to see what actually happened. Some predictions were accurate. Others required adjustment as new data arrived. Throughout, they maintained their careful, probabilistic language that characterizes good forecasting. Could, possibly. Depending on conditions, it's not perfect, but it's honest, and it's the best we can do with a star that keeps its secrets well. For all the technical complexity and potential hazards of solar storms, there exists one effect that is purely, utterly beautiful, the aurora. Picture yourself standing in darkness far from city lights. The air is cold. Auroras favor winter in the northern and southern latitudes and still. Above, the stars shine with crystalline clarity. Then, slowly, the northern horizon begins to glow. At first, it's subtle, easily mistaken for distant clouds or light pollution. But the glow strengthens, takes on a distinctly green hue and begins to move. Curtains of light ripple across the sky as if an invisible giant is shaking an enormous glowing sheet. The curtains fold and undulate, stretch and contract, dance with grace that seems almost choreographed. Rays of light shoot upward, converging toward the zenith. The color intensifies brilliant emerald green, the green of spring leaves, of fresh grass, of precious gems, and if you're particularly fortunate, hints of deep red appear at the upper edges. Mixed with purple and pink at the lower borders, this is the aurora borealis, the northern lights, the visible face of the sun's influence on Earth. What you're witnessing is a visible manifestation of processes occurring 100 kilometers above your head and stretching back across 150 million kilometers to the sun itself. The auroral light you see is produced when charged particles, electrons, and protons that originated from the sun crash into Earth's upper atmosphere at tremendous speed. Here's the remarkable physics. When these solar particles collide with oxygen and nitrogen atoms high in our atmosphere, they transfer energy to those atoms, exciting electrons to higher energy states. When those electrons drop back to their normal states, they emit photons, particles of light at specific wavelengths determined by the atomic physics. Of the gases involved, oxygen atoms produce the green light we see most commonly. emitting photons at 557.7 nanometers when the collision occurs between 100 and 250 kilometers altitude. This is the signature color of auroras, the green that appears in almost every aurora photograph and dominates most displays. But oxygen can also produce red light at 630.0 nanometers, though this occurs higher up above 250 kilometers where the atmosphere is thinner and collisions are less frequent. Red auroras are less common, requiring more intense storms and higher energy particles. But when they appear, they're spectacular, blood-red curtains stretching across the sky, sometimes extending so low they seem to touch the horizon. Nitrogen contributes blue and purple hues. Ionized nitrogen produces brilliant blue light, while neutral nitrogen can create pink and magenta shades. These typically appear at the low edges of auroral displays, below 100 kilometers, where nitrogen is more abundant. The shapes and motions of auroras reflect the complex interactions between solar particles and Earth's magnetic field. The particles don't simply rain straight down. They spiral along Earth's magnetic field lines, converging toward the magnetic poles. This is why auroras form oval-shaped zones around the north and south magnetic poles. During quiet times, these auroral ovals are relatively small, confined to high latitudes. Scandinavians, Alaskans. Northern Canadians, those living in the Arctic Circle, can witness auroras regularly. But during geomagnetic storms, when solar wind energy pumps into Earth's magnetosphere, the auroral ovals expand. The stronger the storm, the farther south and north. In the southern hemisphere, the auroras can be seen. The most intense geomagnetic storms can push auroras down to mid-latitudes. During the May 2020 solar storm, auroras were visible from Europe across the United States, and even from parts of Mexico, a rare treat for millions who had never witnessed the phenomenon. During the great storms of March 1989 and October 2003, auroras danced over Texas and the Mediterranean. But witnessing an aurora is more than just seeing colors in the sky. There's an emotional, almost spiritual quality to the experience that's difficult to articulate. The lights are silent despite folklore about auroral sounds. Most scientists believe the phenomenon is truly silent, though some observers do report hearing crackling or whooshing noises. This silence adds to the ethereal quality. You're watching this tremendous energetic display playing out overhead. This visible connection between Earth and space, and it makes no sound at all. The motion is mesmerizing. Unlike stars, which appear fixed, or clouds, which drift slowly, auroras dance. They pulse and shimmer, swirl and fold, appear and disappear, all on time scales of seconds to minutes. You can watch the changes in real time. An aurora is not a static thing to be photographed and moved on from. It's a performance. An unfolding event that draws you in and holds your attention. The colors, too, possess a quality distinct from any terrestrial light. The auroral green is unlike anything else in nature, not quite the color of plants, not quite the color of minerals or paints or computer screens. It's a pure, atomic emission, the color of excited oxygen atoms 557.7 nanometers wavelength. And there's something elementally satisfying about seeing physics made visible. Time seems to slow down when watching auroras. Minutes slip by unnoticed. The cold becomes less noticeable. Neck strain from looking upward for extended periods fades from awareness. You're watching something ancient. This has been happening for billions of years, yet immediate and present. The sun gave a gift. Earth's magnetic field delivered it to the poles. And you're standing in exactly the right place at the right time to witness the result. Photography has both helped and hindered appreciation of auroras. Modern cameras, especially with long exposures, can capture auroral colors and structures invisible to the naked eye. Time-lapse sequences show auroral dynamics beautifully. Social media has brought aurora images to millions who've never experienced the real thing. All of this is wonderful for raising awareness and sharing beauty, but photographs, no matter how stunning, cannot truly capture the experience. They can't convey the sense of scale, how the auroras arch across the entire sky, from horizon to horizon. They can't show the motion, the living, dancing quality of the lights. They can't capture the emotional impact of standing under the display. knowing you're witnessing a direct, visible connection between your planet and the sun. This is the paradox of auroras. They're consequences of the same space weather phenomena that threaten our technology. The solar wind that disrupts power grids also paints the sky with colored light. The geomagnetic storms that interfere with satellites also enable people at mid-latitudes to witness something they'd normally need to travel to the Arctic to see. In this way, auroras remind us that not all consequences of solar activity are negative. Beauty and danger can coexist, can in fact arise from the same source. The sun's violent outbursts that we monitor with such concern also gift us with one of nature's most spectacular light shows, when active region for 1366 centids CME earthward in early February 2026. Space weather forecasters issued warnings about potential impacts to technology, but they also noted the possibility of auroral displays visible at mid-latitudes. Both warnings and beauty forecasts proved accurate. Power grids experienced some stress but handled it. Radio communications were disrupted. Satellites adjusted their operations, and millions of people looked up to see curtains of green and red light dancing across skies, where auroras rarely appear. For those who witnessed them, the auroras of early February 2026 will be remembered not as a technological threat, but as a gift, a visible reminder that we live on a planet in space, bathed in solar wind, protected by a magnetic field, part of a dynamic system far grander than our daily concerns, and that, perhaps, is the most important consequence of all. Let us now gather the threads of our narrative and examine what actually transpired during those days in early February 2026 when active region for 1366 commanded the attention of space weather watchers around the world. Alpha 366 first rotated into view on the sun's eastern limb in late January, announcing its presence with a rapid growth in size. Within 48 hours, the region had expanded to cover an area equivalent to 6.5 Earths large even by sunspot standards. Its magnetic configuration was complex, with multiple umbrae, the dark cores of sunspots surrounded by lighter penumbrae, and magnetic field lines twisted into configurations that screamed potential instability to trained observers. The first significant flare came on February 1st, an X8.3 class eruption, one of the strongest flares of solar cycle 25 to that point. Spacecraft detectors registered the flash of X-rays. Within minutes, radio operators on the sunlit side of Earth reported blackouts. Coronagraph images revealed a large CME billowing away from the flare site. Analysis suggested it was at least partially Earth-directed. Over the following days, Alpha 366 continued its barrage. An X for point to flare on February 4th, an X8.1 on February 2nd, and X1.5. Multiple M-class flares, events that would be noteworthy on their own, but were overshadowed by the larger eruptions. By February 5th, the count stood at 10 X-class flares and dozens of M-class events. It was an extraordinary display of solar fury, with the region maintaining its eruptive behavior even as it crossed the center of the solar disk. To face Earth directly, each flare brought its own consequences. Radio blackouts rippled across the day side of Earth, briefly disrupting HF communications before fading as the flare subsided. NOAA's Space Weather Prediction Center issued a steady stream of alerts of 3 strong radio blackouts, S1- solar radiation storms, watches for incoming CMEs. The coronagraph images told the story of multiple CMEs launched from Alpha 366, some faster, some slower, some directed precisely at Earth, others at angles that would deliver only glancing blows. Space weather forecasters tracked these eruptions, feeding observations into models, calculating estimated arrival times. The predictions varied: February 4th for the earliest arrivals, February 6th for later ones with uncertainties of plus or minus 12 hours. Typical for such forecasts. Then came the waiting. The CMEs hurtled through interplanetary space, invisible to all but the most sensitive instruments, while Earth prepared as best it could. Power grid operators reviewed procedures. Satellite controllers placed sensitive spacecraft into safe modes. Airlines examined polar routes. Amateur radio operators prepared to document any ionospheric disturbances. Aurora enthusiasts in northern regions hoped for clear skies, while those at mid-latitudes dared to dream of seeing lights they'd normally never witness. The first CME arrived at Earth's magnetosphere on the evening of February 4th UTC, somewhat earlier than initially predicted. Spacecraft at the L1 Lagrange point detected the sudden increase in solar wind density and speed, along with the southward turn of the interplanetary magnetic field, the crucial ingredient for efficient energy transfer into Earth's magnetosphere. The geomagnetic storm that followed was significant but not extreme. NOAA classified it as G3 strong at its peak, with magnetic field perturbations indicating substantial energy input, but not the overwhelming levels that would mark a severe or extreme storm. Magnetometers around the world registered the disturbance. Auroras bloomed over northern Europe, Canada, and Alaska, with sightings reported from the northern tier of the United States, Washington, Montana, North Dakota, Minnesota, and similar southward expansions in the southern hemisphere. Subsequent CMEs arrived over the next 2 days, some reinforcing the ongoing disturbance, others adding their own energy to the mix. The geomagnetic activity remained elevated through February 6th, with periods of stronger and weaker response as CMEs with different characteristics, and magnetic orientations impacted Earth's magnetosphere. The effects were notable but manageable. Power grids, particularly those at higher latitudes more susceptible to geomagnetically induced currents, experienced some stress. No major failures occurred, though operators in some regions took preventive actions to reduce loading on vulnerable transformers. Several satellites reported anomalies, memory errors, brief communication losses, orientation glitches, but none suffered permanent damage. GPS accuracy degraded slightly during the storm peaks but remained within acceptable limits. For most applications, airlines rerouted some polar flights, particularly during periods of elevated solar particle flux when radiation exposure became a concern. The diversions cost time and fuel but were executed smoothly, a testament to well-practiced procedures. Amateur radio operators reported varying HF propagation conditions, with some bands enhanced by auroral ionization while others remained depressed. For those who work radio as a hobby, it was an interesting time, challenging but also exciting, as periods of good propagation allowed unexpected long-distance contacts. By February 7th, the main event was winding down. Alpha 366 continued producing flares. It would remain active for days, but the cluster of Earth-directed CMEs had passed. The geomagnetic storm subsided to minor levels, then to quiet conditions. Auroras retreated poleward. Power grid stress eased. The flurry of space weather alerts slowed to a trickle. In the aftermath, scientists and forecasters reviewed what happened. The event provided valuable data for validating models, testing procedures, and refining our understanding of how CMEs propagate and interact with Earth. It was not a worst-case scenario, not a Carrington event or even close, but neither was it trivial. It fell into that middle category, significant enough to test systems and require response, but not severe enough to cause major disruptions for the public. Alpha 366 was a week of heightened space weather news, stunning aurora photographs on social media, and perhaps a new appreciation for the dynamic relationship between Earth and Sun. For the watchers, the forecasters, satellite operators, grid managers, and scientists, it was both a test and a reminder. Our monitoring systems worked. Our forecasts, while not perfect, were useful. Our response procedures functioned as designed. But everyone involved also understood this was not the big one. Someday, perhaps soon, perhaps not for decades, the Sun will produce something more severe. When that day comes, we will need everything we've learned from events like AR 4366's February 2026 activity. The watch continues as AR 366 continued its journey across the visible face of the Sun, eventually rotating out of Earth-facing position by mid-February. Scientists compiled their observations and data. The sunspot had been extraordinary by any measure. 6X class flares in 72 hours. Sustained activity over more than a week. Magnetic complexity that provided valuable data about solar dynamics. And yet, despite all the concern, despite the careful monitoring and the what-if scenarios, Earth emerged unscathed. The power grids remained stable. The satellites continued their silent orbits. Life continued as normal for the vast majority of people who never knew a giant sunspot had been facing our planet. This is often how it goes with space weather. The potential for disruption exists. The physics clearly shows the mechanisms by which solar events can affect Earth's technological infrastructure. But most of the time, we're protected by distance, by our magnetosphere, by the simple statistical fact that space is vast and direct hits are rare. Alpha 366 reminded us of something important. We live in a dynamic solar system. The sun is not a static backdrop, but an active, changing star. Sometimes it reminds us of this fact. We've become remarkably good at watching and understanding these processes. The instruments we've built, the knowledge we've accumulated, the networks of observers, both professional and amateur, all of this represents humanity's drive to understand the cosmos, and there's something deeply comforting about that. We're not helpless in the face of solar activity. We watch, we measure, we predict, we prepare. We've learned to read the signs, to forecast the weather not just on Earth but in space itself. Alpha 366 eventually faded, its magnetic complexity gradually resolving as the fields dissipated. By late February, it had rotated to the sun's far side, invisible from Earth. Perhaps it persisted there, or perhaps it dissolved back into the churning solar surface. The sun continues its 11-year cycle, approaching solar maximum. There will be more sunspots, more flares, more opportunities to watch and wonder at the nearest star. And we'll be watching, with our satellites and telescopes and networks of dedicated observers, learning a bit more with each event about the star that gives us life. And so our story comes to a gentle close. Alpha 366, the giant sunspot that captured the attention of solar scientists worldwide, has taught us about magnetic fields, solar dynamics, and our place in a larger cosmic environment. We've traveled together tonight from the sun's surface to Earth's protective magnetosphere, from the physics of solar flares to the beauty of auroras, from historical events to modern observations. I hope you've learned something fascinating. More importantly, I hope these stories have helped your mind settle into a peaceful state, ready for rest. The universe continues its dance. Right now, the sun is shining, just as it has for billions of years and will for billions more. Earth's magnetosphere is standing guard, deflecting the solar wind, protecting the thin film of atmosphere that makes our world habitable. And you are here, safe and comfortable, a tiny part of this vast cosmos, taking a moment to understand and appreciate the forces that shape our existence before you drift off completely. If this story has helped you, please consider leaving a like on this video. It truly helps others find sleepy science tales. Subscribe if you'd like more scientifically accurate bedtime stories, exploring the wonders of our universe. And share this with anyone who might enjoy falling asleep to stories about space, science, and the cosmos. There will be more stories, more journeys through the universe, more opportunities to learn while you rest. For now, though, let yourself relax completely. Let the day's concerns fade away. Tomorrow the sun will rise, the Earth will continue its orbit, and you'll wake refreshed, having traveled in your dreams perhaps to distant stars and swirling magnetic fields. Thank you for spending this time with Sleepy Science Tales. Sweet dreams, dear listener. May your sleep be peaceful and your dreams be filled with stars.